Folks are starting to join, so you can get started whenever you would like.
Sure. Yeah, I'll get started. And thank you for attending this session. And today I'm going to talk about how HTAP databases simplify your data infrastructure. And I'm Liquan, and I'm currently a database engineer at PingCAP. And prior to joining PingCAP, I've been working at Confluent and Pinterest, working on big data and stream processing. And one interesting fact about me, I usually tell this joke when I give a talk, is that I never worked on relational databases before I joined PingCAP. But since I joined PingCAP for about 3 years, I can say that I know a little bit about databases. And today I'm going to share a bit more about things on TiDB and the company behind TiDB, PingCAP. So PingCAP is a company behind TiDB, and currently we have over 650 people across the globe, and we are currently in Series D+. We have offices across the globe. We have offices in Silicon Valley, Amsterdam, and Tokyo, and Singapore. So our mission is to really empower the engineers to innovate with speed, agility, and scale. So that is our mission. And the PingCAP's main product is TiDB and TiDB Cloud. I'll talk about those more in the future in the following slides. Okay, so PingCAP has started building from open source since day one. And we have two major projects. One is TiDB, the other is TiDB, and you can see both of them has a big number of contributors and the number of people who are interested in knowing more. And so our product TiDB and TiDB Cloud has been adopted by over 2,000 users in production. And here are some logos that people has been using TiDB in production. And besides those adoptions, we also have a few top tech companies in North America and a few top crypto exchange companies and big banks who is also using TiDB in production. Before I dive into the major topic, I want to do a quick demo about a open source. And actually, this is not our product. And this is demo we built to showcase the capability of TiDB, especially on the HTAP part. And HTAP is short for the hybrid transactional and analytical processing. And this is actually a live demo. And we built this demo using TiDB Cloud. So the goal of this demo is actually to demonstrate the capability of TiDB. And to do that, we actually ingest the data from GitHub in real time. Whenever there's an interaction in the GitHub, for example, if a user forks the repo, if the user file a pull request, or they comment on an issue or a pull request, then there will be an event generated by GitHub in real time. And we actually ingest the data to TiDB in real time. And you can see that it's have more than 5 billion data because we basically ingest all the events from GitHub since the inception of GitHub. And you can see there are something like a Twitter feed. You can see what's actually happening in this in GitHub and some of the stats around the GitHub. So the goal, the major functionality of this tool includes information about certain contributor on GitHub and certain stats on the certain repositories on GitHub. So one interesting thing about this is that either the user and the repo are different dimensions if you think in the database terms. So we can see the stats about a person. This you can think about this as a profile of a person on GitHub, about his contribution trend, about his behavior, about kind of like his contribution history to different repos. You can also understand the the information about a repository, for example, whether a repository is popular and which countries cares most about a certain project. So, and the goal of this insight is to provide maybe some investors whether you should pay attention to a certain trend so that you can find more investment opportunities. So, yeah, I think that is kind of what I want to talk for now. And I think traditionally, if you want to build an application like this, it's not as simple as it sounds because the data we're working with is relatively big. You can see from the demo, it's over 5 billion rows. And there are many applications even have bigger data set. And the typical way of doing this is actually is using a tech stack mostly like this. So we have a relational database or a NoSQL that support the data ingestion and updates. And we typically have things like Kafka or Browser as a way to gather the changes, gather the events from the database, and using some ETL tools like SparkFlink, and then ingest this data to a data warehouse, and then computing the result using the data warehouse, and send the data back to a query, cache, or serving layer, and then display those insights. That's why typically with a company like Uber, like internet companies, they have a big data team, which maybe 20 to 30 people more, that are purely maintaining those data pipelines and data warehouses. So I think if you look at this, I believe it is kind of like a very complex data architecture. Not only those systems needs to be scalable and highly available, but also those data pipelines needs to be scalable and highly available, which actually has a lot of challenges. I used to work at Pinterest. In Pinterest, I worked on building those pipelines. And I understand that it's not really very fun and enjoyable. And a lot of times I spend time debugging the data consistency issues on data pipelines, or I need to make sure that the pipelines are running, and I need to keep lights on. So as a result, with those architectures, complex architecture, it is quite slow to launch some new features because all the changes need to go through this pipeline, and that takes time. And not only this, this architecture is quite expensive. For example, because of each component needs to be highly available, so each component has some building kind of mechanism to achieve high availability. So usually data replication is to use to high availability. And all this system has multiple replicas. So we have this data replicas not because of we need those replicas, because of the complex architecture. It's really a technical limitation instead of kind of the business needs that we need so many replicas in the system. So I think this is not ideal, right? This is kind of this architecture slow down the feature development and also costly. So what is the solution? I think this is basically the answer. You can use TiDB to build that type of application, data-intensive application, providing insights to the people in real time with a single system. In what follows, I will talk about the motivation that behind TiDB and why should you use TiDB to build your applications, and how TiDB can simplify your architecture. So let's dive into a little bit on this kind of the demo I just showed, and we call it the OSS Insight. And the goal is to ingest data in real time and provide real-time insights over the data set. And let's dive into a little bit more. So what questions do we want to answer for those insights? For example, who is a superstar in GitHub? And the second question people may want to know is that who are the popular repositories, which repositories are very popular, so that as an investor, you can think about investing in it. And then which kind of like repository those GitHub stars follows. Those might be some network effect you may want to pay attention to. So these are only 3 basic functionality I want to kind of do some deep dive, and we have more and more complex functionalities actually built into the OSA set application. So let's take a look at the GitHub events. So whenever there's any interaction with GitHub, for example, if you watch, if you fork, and if you start, there will be some like events, and the events something look like this. So for example, it has event ID, and it has a type of event, and when the event is created, and which repo kind of like this event is about, and then who is kind of like taking the action. So this is a little bit like outdated. At the time of the when the slide is created, it's like this is like 406 billion events is already in our database in TiDB, and now it's over 5 billion events. So let's think about how to build a application to support those functionalities. I think the answer is quite simple, right? You typically use a database, and you have application server built on top of the database. And this is very, very easy. So let's look at how this like questions can be answered with the simple architecture when the scale is small. So it's use the GitHub superstar, and one way we look at it is to see the number of events for a certain user, right? So for example, in this simple query, you can just simply count and finding an actor with a login name as TJ is someone. And then this, if you do this and then take an order by on the count, and then you get the popular users. And you can also do some like conditional filtering on these counts to determine whether it's superstar, and this is determined by your criteria. But it's pretty simple, right? You can basically write this query in about 10 seconds. And then which repository are popular. And again, with the simple architecture, it's very easy. You can also write a simple query, select the repo name, and then do a count and group by the repo name, and figure out whether the kind of like the events on a certain repo exceed a certain threshold. If it exceeds a certain threshold, then we call it a popular repository. Otherwise, we won't call it a popular repository. Yeah, this is slightly involved. You probably need to learn a little bit SQL to write this correctly, but still, probably I think you can finish this within 5 minutes. You can write this query, and that's it. And the third question, so which GitHub superstars follows a repository? So this is a slightly more involved, and you can do it by multiple ways, but the one way to do it is first figure out who are the like superstars, and then figure out the repository they care about, right? So this has some like a nice query in it. So this is slightly involved, but still you can finish that within maybe 30 seconds, 30 minutes, or 1 hour. I think one beautiful thing about using a database and SQL is that the SQL is a composable language. You can use those operators provided by SQL to compose arbitrary complex queries to express your business logic. I think this is one benefit of SQL. But the thing is that, as we mentioned, so typically people want to have growth. And when people build up application nowadays, they actually want to have the growth. They want to build for the growth. So I think that's actually caused a lot of problem to the database, because traditionally database is known to be not scalable, and it's kind of quite challenging for traditional database to support large scale data and complex queries. So how to scale? And I think the traditional wisdom is to use sharding. And sharding is also a simple technique. You basically take, like the word mean, right? Shard the database into parts and put different parts in different databases. That is sharding means. So for here, the example, you can shard a big table into three small ones and put them into two database instances. So that's how you shard. And this works because this can handle the data scale as the data scales. But it also poses a lot of challenges. I won't expose those challenges by look at the questions we just talked about again when the scale is small. So in the case of sharding, I want to illustrate that those simple queries no longer become simple. For example, in case of the question is a user GitHub superstar, now it's a little bit involved. It used to be like a simple query composed within 5 seconds, but now it becomes, let me repeat. So one way we can shard is to shard by the user ID, because we shard by user ID, so this query doesn't change, because those queries will only need to go to one shard, and in that shard, we can execute a simple query. So that is easy. So remember that we are sharding by the user ID. But then query on the repository can be a challenge, because now in order to answer this query, because the database is sharded by the user, you actually have to go through all the shards in order to figure out, because you need to count all the because, for example, each shard you need to figure out whether repositories are popular, and then you need to merge those results from different shards and to figure out whether a repository is popular. Yeah, because only you look at all the shards, you can figure out whether a repository is popular. So this is a bit involved. But still, this is not that complicated. But if you look at the third question we just asked, which GitHub stars follow repository? This becomes multi-steps. The first of all, you need to go each shard and figure out which are the local the superstars, and then we need to figure out the global superstars. And then from the global superstars, we need to send them back to different shards and figure out whether they are following a certain repository, and then merge the results. This is a bit complicated. So imagine that those are not very complicated queries, right? They're not really uncomplicated queries people want to know. There can be more complex queries people want to get answers for. And in the sharding situation, those queries will become very, very complicated. And those queries need additional development work on the developer side in order to them to ship those features. And then because it's a combination of SQL query and application code, validating the correctness of those code takes more time. So it's really like sharding, I think, is clear that from the examples, it will reduce or slow down developer velocity. And not only about that, from the maintenance perspective, sharding causes more issues. a simple word is that sharding basically removes not all the a lot of, if not all the benefits of databases. For example, here are just a few issues that I want to talk about. Is that failure needs to be manually handled, and the scale in, scale out needs downtime, and the schema change, because it happens on different database instances, is actually out of sync. And it's really hard to achieve transactions because now you're dealing with multiple databases. And if you want to launch a new feature, you probably need to reshard your database. I think one example I want to give is that, for example, Slack used to shard by the user ID, but when they launched the feature called Slack Connect, which connect two Slack spaces, that truly need to reshard the database and shard by the channel ID. So I think the whole sharding takes time. It may take at least a couple months to have to move a critical or to reshard a critical like database. So what if you don't need to reshard and still has a single database experiences but at scale? So I think this is actually one of the major motivations of TiDB. Try to save the time of developing a new feature and try to reduce maintenance overhead, but still provide nice properties of like databases, for example, like the SQL interfaces and transactions. Yeah, that is basically the motive of TiDB. And what is TiDB? So TiDB is a distributed SQL. And one nice benefit about TiDB is that there's no more manual sharding. From the user perspective, this behaves like MySQL. You can actually using MySQL client to connect to TiDB. They can also use your familiar MySQL ORM, and that mostly work with TiDB. And the TiDB has a distributed architecture, and then because of that, it offers high availability out of the box. And also TiDB offers ACID properties and strong consistency. And from day one, they are open source, and we can be deployed on different cloud providers, on bare metal, virtual machine, and Kubernetes. And TiDB is not a fork, it's not a middleware, it's not a SQL on Hadoop. We actually implement TiDB from scratch. We implemented our SQL layer and our storage server. So here's kind of like a high, maybe 10,000 feet overview of TiDB. So it supports MySQL via protocol. And the application server can use MySQL client to talk to TiDB. And TiDB is built on top of, it's a SQL about NoSQL, and the tables and the data in TiDB actually is encoded in key value pairs. And the data actually stored in TiDB and the TiD Flash. I will talk a little bit more about that in future slides. Here's a slightly kind of deep dive about the architecture of TiDB. So it has kind of like two storage engines. One is a column store and the other is row store. So the row store is TiDB and the column store is TiD Flash. So one nice thing about TiDB is actually it keeps the data in the column store and the row store strongly consistent during read time. So during read time, and that is actually the magic of why TiDB is good fit for building applications like the OSA Con, like the demo, which is a data-intensive application which contains large amount of data ingestions and updates, as well as provide the real-time insights, which usually like complex queries to the user. And the other magic behind the TiDB is the TiDB's SQL optimizer has a feature called Smart Selection. It can automatically choose the data from the row store or the column store, depending on the query. For example, if the query is more likely a point get, it will go to the row store. on the other hand, if the scan over a large time range or large range, we'll go to a column store. And that is automatically handled by the SQL layer. The user doesn't need to be aware of that. So we call this smart selection. And I want to talk a little bit more about the magic we call data auto sharding in TiDB. And typically, from the user perspective, it's still like a single node databases, but underlying we actually has a lot of mini shards. We call them regions or splits. And those regions or splits are the basis for representing data and indexes. So we basically split the data into regions, and those are key value pairs. And you can think about each of them has a 96 megabyte split. It's a logic concept, and each regions are kind of like replicated. So look at the simple table of three fields. It's got employment number and employee name, and then the salary. And actually, those are encoded as key value pairs in TiDB. For example, the key will be the table ID, and the row key. It can be primary key or can be auto-generated like a primary key, depending on how you represent the data. But you can see it's like you have a key here, and then you have the value encoded in the as a value. And then this key value pair, this is key value thing actually sharded or divided or split into regions, which are 96 megabytes. And then TiDB will put those different regions into different TiDB nodes. So you can think here the orange color is one region, and then the red color is one region, and then the green color is one region. Those will be distributed or placed into different TiDB nodes. And this process is also automatic, as a user don't need to be aware of that. And TiDB will handle the data movement if there's a new node join or failover if a node fails or things like that. So this is all handled automatically from the user perspective. They only need to know that there's a table, and the table can, the difference between this table and the table in the traditional database is that this table can be very big. It can contain billions or even trillions of records in this table. And then TiDB will handle the data distribution, data like replication and scalability under the hood. So here are some of the success stories of TiDB. So the first one to talk about is actually Pinterest, and the Pinterest is a big user of MySQL sharding and HBase. I think the reason they choose HBase and MySQL sharding is that when Pinterest is founded, there's no system like TiDB, and then they actually have to either choose sharding or NoSQL at that time. And the reality is that they choose both. But then over time, they figure out like either way it doesn't meet their needs when their business grows, because neither NoSQL or HBase provide the rich like SQL queries, rich like SQL for them to build their application logic. And as a result, if they want to support something even like a secondary index queries, they actually have to build multiple systems to support that. So that will complicate their architecture, and that's also costly. So that's why when they migrate from HBase to TiDB, for some of the use cases that need secondary indexes, they actually see 300 to 500% improvement, and with 80% cost reduction. And if you want to read more about this, you can look at this blog published by Pinterest. Another story I want to share is, so it's really the biggest payment company in Japan. And is very similar to Cash App or Venmo. It's really like a P2P, like a payment. And the core functionality of those kind of customers is really like the fulfill the payment, and then also save the balance in the application, such as a wallet. So you can think about they need to keep a ledger, and this ledger will be growing as the number of user grows. And also they need to keep the ledger in the system for a lot of purposes, for example, audit, distribute, and handle complaints from the users. And also for like compliance and regulatory purposes. So this ledger will go big as the number of users grows. And then for this company, the challenge is that as the number of users grows, so their databases, for example, they were using Aurora, cannot handle the growth. So they can see a lot of like a failed payment, a lot of like outages from databases. And then they are looking for new databases that can handle their further growth. And actually they use TiDB, and use TiDB, they didn't need to change any architecture, for example, separate the cold and hot data, but they can save all the ledgers, all the transaction history, all the and fulfill all the transaction processing within TiDB, and then that actually helped them to scale the user from 15 million to 30 million. And actually now their core functionality is already on TiDB. It's their application, their payment services, their cashback services, and their wallet, they're all on top of TiDB. And the TiDB actually shows higher throughput, lower latency, and high availability. And in production, they have survived even a region failure in the Tokyo region in 2021.
5-minute warning.
Thank you. And it's about to finish. So this is a leading CRM, and I think CRM is, in my opinion, one of the probably the most suitable cases for an HTAP database. So why I say so? So I think the CRM or the SaaS actually start from Salesforce, right? It's a CRM. And you can think about the user of CRM are sales reps and sales managers, right? And also they provide in a way in the cloud so that the users don't have to deploy the CRM in their own data center. So from the CRM provider's perspective, the SaaS provider perspective, they need to manage a lot of data from different users. And the traditional wisdom also be sharding, right? But the CRM has a lot of functionality like ad hoc queries. For example, sales manager may want to know which reps are performing good or bad, or the progress of deals in real time. They probably want to run some queries and then expect the queries to finish within a couple seconds or even less. So they actually need those capability to run ad hoc queries and run some complex queries, because if you want to understand the reps performance, you want to do some order by, you want to do some aggregation, and that is not very handled very well by MySQL sharding or SQL sharding or NoSQL. So as a result, they choose to use TiDB, and you can see that TiDB can perform much better compared with MySQL. You see over 30 times performance improvement of TiDB. So here I want to conclude is that I think architecture is actually the enabler of a lot of business opportunities. And with TiDB, you can actually simplify your architecture and provide the real-time insights using a single database. And I think here's the takeaway. I think if you want to remember anything I want to talk about, I think this is the picture probably you want to remember. And traditionally, if you build an application that provides some real-time insights, provides some you need a very complicated architecture, involving multiple components and the compliance, how to maintain ETL pipelines. But now with TiDB, you can do everything with a single database. And you want to see the magic about it, I encourage you to check back again to the OSA site. And I want to just quickly show one query, which is the trending repos of past 24 hours. You can see this is supported by queries, a relatively complex query. And if you look at the query plan, you can see this query is served by the row and column together. So that's actually the beauty of database, the HTAP database. You can actually choose where to read the data from, depending on your query pattern. And this will conclude my talk. Yeah, and thank you for your attending my session.
Great talk, Liquan. Thank you so very much for joining us and sharing all of this with us today.
Thank you for your help. Yeah. Any questions?
Nothing in the Q&A at the moment.
Okay, cool. And thank you for the attendees and our job.
Great. Sounds good. Thank you.
Thank you. Bye-bye.
Bye-bye.